CLion, a cross-platform IDE for C and C++. Download now.
Hi everyone, my name's Dave Rowland. I am the CTO of the Audio Squadron Group, and we're an audio technology company. We have two main brands. Our Prism Sound brand makes high quality audio interfaces and large channel count converters for big studios. And on our software side, we have our Traction brand, which makes a whole bunch of weird and wonderful software instruments for creating music and compositions for film and television, etc. And we also have a digital audio workstation, which is a sort of multi-track recording program called Waveform. And the back end of that, which is the real-time elements and the data model, kind of the tricky C++ bits, are part of an open source project called Traction Engine, which we license to other manufacturers to put their own UI and UX front end on. So a bit of background for why I'm giving this talk today. Several years ago now, me and Fabian Rengiles gave this talk at Meet in C++ called Real-Time 101. We gave a slightly longer version of it a couple of weeks later at the ADC conference. And it was designed as a sort of really kind of whistle-stop tour introduction to real-time programming, and kind of gave you hopefully a decision chart that you could ask a question of what requirements you had of your system at each point, and then give you to a kind of existing paradigm or solution that you could draw from. And I've chatted with Fabian since several times, and we always thought that it was a great introduction to the topic, but there's always a bit more to be said. So Fabian followed up a couple of years ago at the Audio Developer Conference with his Real-Time Confessions talk, where he kind of filled in some of the areas that he thought could do with a bit more detail and explaining. And one of the areas I always thought we could talk more about was the lock-free queues aspect. Now, we did mention it. We had this idea of blocking versus non-wait-free or lock-free and then wait-free. We showed the sort of classic circular picture of a FIFO. We showed a really simple implementation of a FIFO, and then Fabian discussed how you could get different behaviors from his farblock queue depending on how you configured it. And that was kind of it, really. It was only about 4 or 5 slides. So if that's all there was to say on the topic, why are there so many different lock-free queues out there? And you can see several from the same supplier. So perhaps there's actually more to this story. And of course, every story has a beginning, so let's start there. Firstly, what is a queue? Is this a queue? Well, I guess in some sense of the word, it's a queue. What about this? That's a bit more how we recognize a queue, but the important idea here is that the people who arrive first to the grand opening celebration will be admitted first. So that's what we mean by a queue, first in, first out semantics, not the opposite, which is last in, first out, often referred to as a stack in computer programming. So what are they used for? Well, certainly thread-safe queues are used for transferring data between threads. And in the audio industry where I come from, they're used a lot for receiving input from your audio interface. You might be then recording those to disk. You might be processing them to put back out to your speakers. MIDI messages or note events come in on their own thread, and you need to put them into your audio graph playback. Metering levels that are calculated and then shown to the users need to come back out of your audio real-time threads. And also these days with multiple cores, you might have cooperative processing, so multiple threads doing your kind of work. And also network data. You can have other event types like open sound control that comes in as UDP packets. So you might need to react to that and get data into your playback system. And then smaller things like DSP filter coefficients, and sometimes your entire playback graph is kind of moved around the system in a lock-free queue. It's also used all over the place in non-audio. A couple of quick examples, a lot in trading systems, and particularly for login data, you need to get kind of out of your real-time path to a slow path. And then inside the kernel as well, these are used to kind of move data around a lot without holding up other parts of the system. And then also you build on top of lock-free queues, kind of different abstractions. Task queues is one of those examples. So why can't we just use locks? Why are we talking about lock-free queues today? Well, locks involve system calls, and system calls, or they can involve system calls, and system calls are unbounded usually. So that means they're not real-time safe. We don't know how long a system call is going to take to return to us because we don't know what else is going on in the system usually. And these days we can verify a whole chunk of behavior or catch it at runtime with RT-SAN or real-time sanitizer. So as that kind of becomes more pervasive, hopefully it's a bit easier to catch when we're using non-real-time safe code. So why can't we go kind of one step up, not into the kernel with a system call, but just stay in user space and use a spin lock? This is effectively just busy waiting on an atomic Boolean. Well, this comes with its own problems. Firstly, you have thread starvation, where one thread might be trying to access the lock, but just because of the way the threads are scheduled and the timing, it can never actually access that lock and therefore can't make forward progress. That's called thread starvation. You can also have priority inversion. So if you have a low priority thread, maybe a UI thread that has gained the lock, and then a high priority thread that tries to come in and acquire that lock as well, it's effectively being serialized at this lower priority, and that thread may have been put to sleep. Worse, the operating system might see this behavior and deprioritize that high priority thread because it knows it's contending with a lower priority thread. And the other problem is that they really just don't scale. Because you have this kind of single contention point on the lock, the more threads you throw at this problem, the worse that serialization point. So if we think about the behavior that you can sort of specify for your even the simplest case of a lock-free queue, which is the single producer, single consumer, you can start to see how you get different behaviors for, say, push, for example. You could either just block as the as you're trying to push an item on and just wait for some data, if it's full, some data to be removed in order to make some space. You could overwrite when it's full, so just ignore the data that's in there and write some new data. Or you might have failure modes where you try to put some data and then report back if that wasn't successful. And the same on pop, you might just block if there's no data available, or return a default value, or fail. What about the capacity? Is it a sort of static compile time constant that's evaluated during compilation and it can't be changed at runtime? Or is it a fixed runtime value that is set upon queue construction? Or can the queue grow? Can it allocate over time if you need more capacity? What about bulk operations? Can you only push a single item or multiple items? What about the size of that item? Is it fixed, like just a single type, or is it dynamic? Can you put in multiple bytes and then read out multiple bytes of different sizes? Is there a limit, an upper bound to the size of the items in the queue? There are examples where you have this, or can it be effectively an object or a type of any size? And what about the triviality? Do these types that you're putting in the queue have to be trivially copyable, or could they be non-trivial? And then what guarantees, depending on these configurations, does the queue give you? Is it blocking? So it might have a mutex in it. Is it lock-free, or is it wait-free? And we'll dig into that a little bit towards the end. And then you have how many processes can your queue be used within? Is it just for use inside a single process, or can you send data to another process using it? And when you multiply up all these sort of behavior decisions, that's how you get to the sheer number of lock-free queues that I showed previously. So that's it. Thanks for coming. That's why there's so many lock-free queues. Well, the reason I gave this, or decided to propose this talk, was because I thought I don't have to write a lot of code here. There's lots of lock-free queues out there. I can just look at those and draw some conclusions and show some examples. But cut to 2 weeks later, after kind of getting accepted for the previous time I gave this talk, and I've written 20 lock-free queues over my 2-week holiday. So the reason I did this was so I could understand what the various techniques are and also create some hopefully good slideware. So join me in this journey of madness of writing all these queues in such a short space of time. Couple of warnings though, there's going to be a lot of slides with atomics and benchmarks on, but try not to get too bogged down in the details, right? Just try and sort of absorb the general ideas and patterns that I'm discussing. The complexity is going to go up in the middle, but there is a bit of a tail off. So don't leave halfway through because you think it's going a bit fast, perhaps. The bad news is we've done the easy bit, okay? So strap in, it's about to get more detailed. A few sort of caveats around what I'm going to show, because I'm showing a lot of micro benchmarks, and like all statistics, they can be misleading. You can sort of create them to show anything you want, really. And we'll see what I mean by that a little bit later. But for this example, at least the first half of the talk, they're idealized to show the impact of the queue. And this means I'm just storing and pushing the smallest amount of data, really, just an int, and then pushing it and popping it off the queue. No kind of big objects here. In practice, depending on what you're doing with that information, the item that you popped off or pushed on that was generating that item, and what else is going on in your system, has a big impact on performance. Could be that something else is completely trashing your cache the next time you come around to use that queue. And also, all the benchmarks are done on my M2 Mac machine, and they're all within a single process. There's a couple of interesting points here. One is this is an ARM architecture, which will become relevant. And also, when we deal with multiple threads for the multiple producer, multiple consumer side, I'm always going to use 4 threads each side. And the idea there is that they can each have a dedicated P core. So I'm not using the efficiency cores. So we need some kind of setup for our benchmark, and I'm just going to run through it quickly. I'm using Google Benchmark, so you can perhaps recognize the boilerplate here. And we're going to get the size of our queue as one of these benchmark parameters. So I was typically dealing with queue sizes of about 16,000, about 44, and 88. So in audio terms, that's about half a second to a couple of seconds. So the general size of queues that we use. And then we're going to say we're going to try and push and pop, iterate round that queue 4 times. So for each benchmark iteration, we're going to construct a queue and then push items into it till it's half full, and that will become relevant. Then we're going to do our timing. So we're going to just push, pop, push, pop, push, pop 4 times around the queue, and then use Stud Chrono's steady clock, which is encapsulated in this stopwatch class, to time how long that took. That means we can set the iteration time to that duration. And then once we've got the number of items that were processed by Google Benchmark, we can multiply that by the number of iterations to get a throughput, a number of items that traveled through the queue per second. And we want to start with a kind of serial baseline. So just within a single thread here. And this is the queue that we're going to use. It just has a capacity, a vector to store the data, and then a head and a tail counter. And you'll see this pattern kind of recurring, but what we do on a push operation is we read the current tail, we calculate the next index with this function, which just increments by 1, and then modulos with the capacity to wrap it around. And then if that index is equal to the current head counter, then we know the queue is full and there's no free space, so we just fail and return false. Otherwise, we can read in to that index in the data and then increment the tail and return true. And the same on the pop size, we just read the head, and if that's equal to the tail, we know the queue is empty and there's no items to return. Otherwise, we can read from that index and increment the head. Now, the FIFOs are often kind of depicted in this round shape, but we know that's not what memory looks like. It's contiguous and linear. So let's create some visualizations to show that. So our initial state of our queue is this, where our tail is equal to our head, and therefore it's empty. And then, as I mentioned, we want to look at the next index, see if it's free, write the item, and then increment that tail counter. And we're going to get to this halfway point and then start timing. And then we're just going to push, pop until we get to the end and then wrap around. And the tail does the same thing. The head, when it gets to the end, it will wrap around as well. And then the other scenario that we have is when the queue is full, you'll see the tail counter is at the end of the queue, but it's going to look at the next tail position and see that that's equal to the head and therefore it's full. And what that gives us is that the capacity, the number of items we can store in the queue, is equal to the size minus 1. And if we do that just in serial, no multiple threads benchmark, we get 183-ish million items per second traveling through the queue. So, that's a number. And you can see this red line at the top. That's the difference between the different queue sizes. So it's fairly negligible, which is why I've combined them all like that. Okay, so we want to deal with multiple threads now. So the easiest way to do that is by adding a mutex. So we can add this mutex and then just use a lock guard in the push and the pop functions to avoid data races between any of the elements, basically. And now we have multiple threads. We need to switch up our benchmark harness a bit because we're going to create this queue thread for the producer and the consumer side. And we're also going to take a latch and internally start a thread, and then all of these producer and consumer threads will kind of reach this latch and then all be set off in one go. Now we're going to start our stopwatch just like we did before, and depending if we're a producer or a consumer end, we're going to do either that try push operation or try pop like we did before. Now there's a lot of empty space here. That is actually empty space at the moment. We'll fill it in when we change up our benchmark, but all we're doing is pushing and popping as fast as we can, basically. Then we're going to take that duration and store our run result, which will pass back on when all of our threads have finished. And if we do that benchmark using a mutex, we can see we've kind of destroyed our performance here. Even though we've got a producer thread and a consumer thread, the throughput is about 20% of what it was. So maybe we're paying the cost of lots of system calls. Maybe we move into user space and use a spin lock. So this is sort of my right of reply, because we got a bit trolled by Eric Rigtop for the really basic spin lock we showed in Real-Time 101, which was just spinning on a ball. That's not the way you do it. He wrote a blog post where he kind of called this out and said, well, actually, the way to write lock-free queues is by relaxing memory order and using CPU pause instructions. So the idea that he presented was that you do this sort of optimistic test and set with an acquire memory order, and we'll dig into memory order a bit later on. But that's a sort of slightly heavier weight option, and then fall back to this relaxed memory ordering, spinning, trying to get the lock, and omitting CPU pause instructions, which are architecture specific instructions that effectively tell the CPU, I'm not really doing anything. If you can do any other work at the same time, go ahead. There's different ways of building spin locks. Fedor gave a version at CPP Now in a lightning talk where he has a similar idea, except for he does the relaxed order load first and then falls back to an acquire, but also has a sort of exponential back off, as well as the kind of micro sleep or CPU pause instructions. So depending on your use case, you might get one of these might work more or a variation of. So let's look at the throughput of that. It's about half what we had before. So even worse than using mutexes. That does seem odd. So maybe we do need to reach for lock-free to get our performance back here. And the simplest way of doing that is taking the queue that we had at the beginning and just making our head and tail counters atomic size t's. So now everything works the same as it did before. It's just that one small change. And if we see the throughput of that, we can see it's roughly the size of our mutex queue. So, we're better than using spin locks here, but we're still not better than using locks. That's strange. So maybe we can look at our queue and see if there's places we can optimize. So the first thing we can notice is that we're using this modulo capacity here, and that's a divide, which is quite a costly instruction, certainly more costly than a multiply, add, or perhaps something else that we'll see. So if we make our queues a power of 2, here we have 2 to the power 3, which gives us a capacity of 8, we can calculate a bitwise mask by subtracting 1 from that capacity. And that mask will be all ones. And then we can use that instead of a modulo to mask with our head and tail counters to do that wraparound. So if our tail is at 7 and we increment 1, which would be 8, and then mask with our bit mask of capacity -1, we'll get 0, which will do the wraparound for us. And a bitwise ampersand is a very fast to do on a CPU. So we could do that trick, which will wrap around our head and tail counters. There's something else we can do though. If we make the queue even smaller for demonstration purposes, just 2 to the power 2 here, we can, rather than actually wrapping around those head and tail counters each time, we can just increment the counters off into infinity. We call these sort of monotonic counters. And then only when we want to find the index we're accessing into the data do we need to do this bitwise mask. So the counter can just increase, and then we just mask it to wrap it around. And this also gives us the interesting property that we can find the size of our queue, how many items are in it, just by subtracting the head from the tail. So here we can see that the queue is full, and then if we pop an item off, we can see that space decreases, and then as we move towards the counters being the same, we know we're in the empty state, even though the indexes are down in the data range. So the question that always occurs when you talk about these monotonic head and tail counters, or any counters really, and they happen a lot in lock-free programming, is will they wrap around? And to get a sort of intuition about that, we can do a back of the napkin calculation. So we have 2 to the power 64. We're using 64-bit size T's. So that's the number of possible values that we can get. Now, if we take our best throughput so far, that was our kind of serial queue of 183 million items. We divide those by each other. We can work at that rate for over 3,000 years, incrementing these counters. So it's unlikely to be a problem. Your hardware is much more likely to fail in that time. However, if you have higher throughput, or you're building a space probe that's got to last for hundreds of years, something to bear in mind. So we can apply these optimizations now to our queue. We use bitsil to find the next power of 2, which we're going to modify our kind of capacity argument. And then when we want to find the index, we do this bitwise masking with the capacity -1. And you'll see the store to tail and head below are always just incrementing by 1 each time. And if we see the throughput here, there's a tiny little performance bump, but not as much as we thought. So maybe that was a kind of not the best approach. Let's rewind, go back to our baseline queue, and take a different fork of optimization. And for that, we're going to talk about memory ordering. Now, I haven't got a lot of time to talk about the details of memory ordering, but if you want an introduction, I would definitely recommend Timur's talk on demystifying stood memory order. Gave it ADC and I think a couple of other times, so you can probably find it on the internet. And if you want a deep dive, Herb Sutter's Atomic Weapons from about a decade ago now is still a really good kind of background overview. The important thing to recognize here, though, is that the code as you write it is not executed in that order. So code reordering can happen at any time. It can happen during the kind of initial compilation phase. You can get things hoisted out of loops, const propagation, that kind of thing. And then as the optimizer actually compiles to instructions, you can get all sorts of reordering, like joining together loads and stores, because it's more efficient to generate those instructions. And also, as the CPU generates microcode from that assembly, there's more reordering going on, and just the pure architecture, like having write buffers or store buffers that will group together writes so they happen in a block rather than kind of interleave with the rest of your instructions. So because CPUs can be multi-cored, you can have all of those different things happening on different CPU cores at the same time. And in order to make sense of that, we have the C++ memory model. So that defines the rules for how multiple threads can access shared memory, specifying when writes by one thread become visible to other threads and what synchronization is needed to avoid data races. So it gives us the rules and also the tools in order to write correct multi-threaded programs. So here we go. Memory ordering on a single slide. There's 3 memory orders. At the lowest level, we have the relaxed ordering, which only guarantees atomicity, so no torn read or writes on your variables. You do get a slight ordering guarantee, which is that within the same atomic variable, stores will always be visible in that order. So if you have an integer atomic that starts at 0 and one thread increments it by 1 and then increments it by 2 to 3, another thread can never read the value as 2. It will always see the increment by 1 and then by 2 in that order. And these are typically used when you don't really care about the timing of things. You're just sharing something between threads. Perhaps it's an exit flag for a thread. On top of that, you have acquire-release semantics, and this is when you're trying to synchronize 2 threads with each other. They work in pairs, so stores have a release memory order and loads have an acquire memory order. And these allow some reordering. They conceptually work as sort of one-way fences, but instructions can either be moved above or below them depending whether it's an acquire-release operation. But how you can sort of think about this is that writes before a release store become visible after an acquire load in another thread. And the way we talk about this is it establishes a happens before relationship. And then on top of that, you have sequential consistency, which is the strongest level. That's effectively a full fence, so instructions can't be ordered above or reordered above or below a atomic operation with sequential consistency. And what this means is that all threads will agree on the order that operations happen in. You can conceptually think of this as kind of interleaving all of your thread operations with the sequentially consistent accesses and atomics as your sort of interleave points. Now, I say these are sort of implemented like read-write locks on the cache line, which will become important later on. In reality, it's much more complicated than that. But if you can think of things like release stores as having to take exclusive access of a cache line, you can sort of think about the performance implications a bit easily. So let's try applying this to our queue and seeing where we can get these or we can reduce the memory ordering. Now, the first thing we need to do is pair up the head and tail loads and stores between our 2 threads. So we do an acquire load and a release store on the head, and then we do the same for the tail. The other thing we can do is use a relaxed memory order for the initial loads for the head and tail. And that's because the store to that variable happens within that thread. So because we have the as if rule, we know that that thread will always have the most recent value. So we can use memory order relaxed here. And if we look at the throughput of this, we can see that gives us basically twice the performance that we had from our V1 queue. So let's try and put this all together. We're going to use the power of 2 and bit mask, the monotonic head and tail counters, and memory ordering. And if we do that, we get another sort of significant bump here. So we're making good performance gains at each step. So is there anything else that we can look at? Well, remember I said release stores work a bit like a write lock on the cache line. And this sort of leads to the problem of false sharing. So when one or more variables share the same cache line, the CPU effectively has to lock access to that memory until it has been used by a single core. Like I said, it's a bit more complicated than that, but that value has to be propagated to the rest of the cores. And if we see in our queue where this happens, the way it's laid out means our head and tail counters are very likely to occupy the same cache line. So here is our queue. We've got our capacity, our data, which is a pointer and a size t, and then our head and our tail. And what the standard gives us is this hardware destructive interference size, which is effectively the size of a cache line. And if we align our head and tail counters to this, we can space them out so they're actually on separate cache lines. So now reading or writing to one shouldn't affect the other. And this gives us another kind of small but significant performance bump as well. So at this point, I thought, well, I've made some good performance gains. We're way better than using mutexes now. What is the state of the art? How do we compare to that? So I pulled in a bunch of other queues, including Rigtops, Farbot, the Moody Camel, and Choc, and then compared how we are on that. So we're kind of there or thereabouts, but a bit to go for most of them. And then there's this Moody Camel reader writer queue, which is 3.5 times quicker. So that's a real standout. So maybe there's something going on there. So there's another trick we can do, which is to cache the head and tail from effectively the opposite side. And what that does is it gives either the producer side or the consumer side a snapshot of how full or empty the queue is. So what you can then do is, without ever reading the atomic that is being written to by the other side, is know that you're free to push a bunch of items or read a bunch of items before having to go back to that atomic. And we can see that we just use that cached head here, and only when the queue looks full from the producer side do we then go and try and reload it from the atomic, and the same on the other side. And if we look at that, there's a bit more variance depending on when those snapshots happen, like how full or empty the queue is. But we can see that's actually quite a significant performance improvement. And it's now much more level with some of these other queues. And I think I mentioned earlier on that we're starting with the queue half full, and that lends itself particularly well to this kind of optimization, because the snapshot in theory should be, well, I can just read half the queue before ever having to look at that other atomic. So at this point, I thought, well, I've got a queue that's fairly well performing, but why is Moody Camel so much better? And Moody Camel takes a slightly different approach. It doesn't use acquire release semantics, it uses explicit memory fences instead. So if we look at how we might go about that, we can take our code, and the first thing is we make all of the loads and stores relaxed. Okay, so you can see all of these are just memory order relaxed. They are shared between threads, so they need to be atomic. Okay, but what this does is destroys the ordering. Because they're relaxed, this store to data could be reordered after that store to tail, so they could be introduce a data race, or it could happen before we load from the head. And on the so what we need to do to fix that is have some explicit memory fences. Now, acquire fences act as a barrier where instructions can't move above, and release fences act as a barrier where instructions can't move below. So this effectively pins that store to data within those operations and stops the store to tail happening before the load to head as well. So we do the same thing the other side. We'd want to stop that reading from data from happening before the load to tail, and we want to stop it happening after the store to head as well. So we introduce the same set of memory fences here. And if we compare the performance, we can see that gives us that kind of huge bump there, which is actually a bit counterintuitive. I wasn't expecting this, because in theory, fences are more restrictive than just using an acquire release operation. Now, why does Moody Camel still have a performance above us? Well, it uses some platform in specific tricks that mean it's not fully portable, and for that reason it can kind of eke out a bit more performance within itself. Now, I gave a version of this talk in October, and that was sort of when AI programming with AI was becoming really commonplace, and it was the first time I wrote a talk where those kind of tools were available. So I thought, well, let's see what the AI has to say about these things. So not on any of the examples I've given, an example that I was kind of unsure about, I said, does this code have any soundness issues? And it would come back and say, this code is sound, it will work correctly, but the acquire fence and the else branch, which I had at that point, is redundant and can be removed. And then I could push back and say, but what if the queue's not empty, and sort of explain my position about why I put it there in the first place. And then it would come back and say, well, actually, now when you read it, it's fine. But then say, hang on a minute, is that true? And I think we've all seen this by now. Actually, you've identified a real concern. Let me reconsider. Then it tries to set up some examples that is quite useful, and then changes its mind and says, actually, let me think about this more carefully. No, here's why it is sound, and then gives me a reason why, and then kind of reiterates that to me. And this, I felt, was very similar to how you might deal with a colleague doing, just asking for a code review. You might say you don't expect them to fully understand everything that you're just bringing to them, but you do expect them to be able to push back, ask questions, maybe, set up scenarios that help you understand your code better. So I think it's still a useful exercise. And a few days ago, I thought, well, AI's moved on a lot in the last 6 months. Let's try that exercise again. So I took the same code and then gave it to Opus 4.6 with extended thinking. And it essentially said, yes, it's fine, and then quoted the bit of standard that that it relates to. So I could go and look that up or ask it to elaborate a bit more. So it's a much more condensed example, and it gets to the solution more quickly. But that scrutinize synchronization patterns bit at the top is a thinking statement, and that's doing a lot of heavy lifting here. If we expand it out, we can see it actually runs through a very similar thought process to before, except for it does it all internally. And there's a lot to kind of unpack there if you really want to. Just an interesting example of how AI has kind of moved on and how it can still be useful to us. So this is the state of play using the benchmark that we've discussed. Okay, we've got our version 6 queue, and then the one using fences, and then a couple of others that are available. So now at this point, I'm going to switch up the benchmark to not just pushing and popping it in. We're going to try and simulate some work. And to do that, we're going to fill in that empty space that I had at the start. So now we're going to try and time, using stood chrono steady clock, how long a push and a pop operation take. We're going to keep a running sum, which I use for testing and validation. And then we're going to also add that time to this kind of running result, which is going to keep a minimum, maximum, and an average, so we can calculate things like standard deviation. And we're also going to keep the number of the number of successful pushes and the number of failed pushes. And the same on the other side here for the consumer side. We're just going to do the same thing. So we've now got more information about the behavior of our queue, and we're simulating a bit more work. And if we do that, I can actually overlay the results here, and we can see that we've destroyed the performance of our queues. Okay, we're about 10% of the throughput that we were before, just by doing some multipliers, a couple of divides, and some adds. It's a very small amount of work there. And the other thing is, if we normalize this up, we can see all those big variations that we had are now essentially destroyed, right? Our version 6 is as good as our version 8, and the same with Rigtops and Moody Camel, right? They're all basically the same now. So that was level 1, okay? Single producer, single consumer. Let's move on to level 2, the single producer, multi-consumer queue. And these come in various forms. They're used as building blocks for things like command queues, worker threads, and some of the things I mentioned before. Now we have the same behavior choices that we made before, but now because we are having multiple threads, we have to think about, can there be multiple producers? Can there be multiple consumers? And also, is there a max number or an upper bound on the number of threads that can either be used at one time or ever be used with that queue? Maybe they keep the thread IDs and never clear them. And then also, is there a strict global order, or is the order of operations on that queue relaxed? And I'll explain what I mean by that. So here's how we turn our single producer, single consumer queue into a multiple producer, multiple consumer queue. What we effectively do is we have to create this compare exchange loop where the consumer side is trying to claim a slot for it to read from. So it reads the current index and then says, right, I want to increment it from that index to the next index. And if it's able to do that, then we can successfully read that data. If it wasn't able to do that increment, then it means another thread did it. So that compare and set failed, and we have to go around and try again. So now we have this loop involved. And what that means is we've introduced a very subtle bug. Now, some of you may have spotted it, but if you haven't, this is how it presents itself. Imagine we have this set up with our small queue again. We're going to increment the tail and wrap it around, or at least wrap around the index. The counter is going to be monotonically increasing. And then we have a consumer thread that's going to try and claim this index number 2 to read. So it's going to do its increment and say, yes, I was able to do that. I can now read from this data. But that might take some time. At this point, another thread can come along and say, well, I'm going to consume some items. It's able to do that. And now, because it's incremented that head counter, the producer side sees that the difference between the tail and the head counter shows that there's an item free or a slot free. So it can go ahead and write into that slot, and then the read from the original thread might finally happen, and it reads the new data, and that original old 44 is just lost forever. So we've introduced a bug doing this. So one way to fix this is to kind of separate the view that the producers and the consumer has. And we do this by having a pending head, which is what the consumers use, and a committed head, which is what the tail sees. And the idea here is that we have this additional inner loop where each thread is trying to perform or commit its read for the slot that it claimed. And what this means is they have to do this in order. So the thread that comes across first has to, any threads that come after have to wait for the preceding threads to commit their values first. And if they're able to do that, that's fine. Otherwise, it means another thread is in the process of trying to commit, and we have to just wait for that to happen. So again, in an animation, we can see this as one thread increments the pending head, and then another thread might come in and say, I'm going to read this data, increment the pending head, but now it has to wait for the original head operation to be committed. And if we compare the performance of that to some of the other single producer, multiple consumer queues out there, we can see that we've got a bit of a way to go. So maybe that serialization point where you've got the consumers kind of all trying to do their commits at the same time, maybe that's a problem. So there's another way we can do this, which is with sequence numbers. And the idea here is that each slot now doesn't just contain your payload data, it also contains an atomic sequence number. And you initialize your sequence numbers as the counter just monotonically increasing. And if that's equal to your tail counter, it means that slot is available for writing to. So that the producer can come in, write to that slot, and then it increments that sequence number by 1. And that offset by 1 indicates that it's available for reading. So it could come along, write some data, increment the sequence number by 1 each time, and then the monotonic counter increases, but we kind of wrap that index back around to the top. So now the counter is pointing at 4, but the sequence number of that index is actually 1. We know that we can't write into that. So a consumer thread can then come along, try and read from the slot, and it can say, well, it's offset by 1 from what my head counter is, so I can read that data, and then it's going to increment it by the capacity -1 of the queue. And now it's equal to 4, it puts it back into that write state because that is the value that the tail counter is pointing at. And we can just go on like this. I'm not going to dig into the code too much because it's fairly similar to what we've seen before, except for now, rather than just storing the T's, we have a slot which has a T and a sequence number. And we have to initialize those sequence numbers before we can start using the queue. And then it's basically the same. We just find a slot and then read the sequence number and act on that. And if we compare the performance, we've got no gain there, which is unfortunate, but perhaps not to to be, it's to be expected because we've only got a few threads working on this queue here. I imagine as you scale this up, that will have more of an impact. So can we do anything else to optimize this queue? Well, we can add this caching back in, but we can only add it on the producer side now because the consumer has multiple threads that we can't share a non-atomic cache because that would be a data race. While one thread's trying to update the cache, another thread might be reading it. And if we apply that, we can see we get a nice kind of performance bump here. So, the tricks that we learned in level 1 still apply to level 2 to some extent. So that was level 2. Let's move on to level 3, which is multiple producer, multiple consumer. Now, I'm not going to discuss this too much because the code is basically the same as what we've already seen, apart from you can't do that caching trick now on the producer side either. Because, again, it would be a data race if one producer thread is trying to update the cache while another is using it. You might see in some APIs things like producer and consumer tokens that a thread needs to create in order to use that queue. And one of the uses for that is they can keep their own kind of per thread cache and then kind of take a snapshot and see what they can use from it. So what I want to do now is compare different types of queues and see if there's anything we can learn about that. So here we're comparing the throughput between the level 2 queues and the level 3 queues. I'm not going to keep saying S, single producer, multiple consumer, because I'll get it wrong at some point. But what we can see here is the throughput is roughly the same, except for it's actually a bit worse on the multiple producer, multiple consumer side, which is kind of counterintuitive because we should have 3 more producer threads, so you would expect the throughput to be 3 times as much, right? But just the added complexity of having to make this work in terms of multiple threads introduces a performance degradation. And when we're not doing much work with those values, remember all we're doing is kind of keeping this running some and doing some timing, you can see that we actually get that degradation of a more complex queue is relevant. Now we're going to take the best performing multiple producer, multiple consumer queue that I did and compare it to a couple of others. Now, first of all, we're going to look at the Moody Camel concurrent queue and then afterwards the Farbot queue in its _WF configuration. So if we first look at Moody Camel, within the documentation, it explicitly says that there's no strict ordering to the operations that happen within this queue. Effectively, what that means is because it uses relaxed atomics for everything, when you push an item into the queue, another thread can't know that it's visible straight away. And that means that you can't ask for the size of it. So it also states if you want to be able to query the size of the queue, you have to keep a track of this yourself. So we could do it by, this is my wrapper around concurrent queue, just to give it the same interface for benchmarking. But if we want to be able to ask the size, we have to have this atomic size T that we can increment and decrement every time we do a push and a pop. Now that means we can ask the size of the queue, how many items are in there, but we can see it has a noticeable performance degradation. And this kind of is just one example of every time you make some changes to your queue in order to provide some additional behavior, it's probably going to come at a cost. So pick the queue that has the guarantees that you need because it's likely to be the best performing one. Now, to dig into why this Farbot in wait fee configuration has such high throughput, we're going to look at some different metrics. Here we can see the number of, or the percentage of failed pushes and pops. So this is when the queue becomes full or empty and a thread is either trying to push or pull, so we get a failure. And you can see on the left-hand side my queue, and how I engineered this benchmark was so we never run into that position. So I'm actually probably performing kind of better in this benchmark than you would in real life. The other thing you can see is this Farbot with the WF also has no failed percentage of pushes and pops. And we can see why, what drives this queue getting full or completely empty and failures occurring when you have a mismatch in the average time between a push and a pop. Now, if that level is quite small, like you can see on the left-hand side, you don't ever fill or empty the queue. If you see, however, the queues that have a big difference in the average size, they fill up or empty. Now, if we had more iterations, I'm sure you would see this with any kind of discrepancy on the producer-consumer side. The interesting thing is, though, if you look at that farbot wait-free, there is quite a big discrepancy between the push and the pop. Now, that WF, as I just alluded to, means it's in its wait-free configuration. And the way it implements that is it says, well, if you push, I'm just going to let you overwrite some data that was already in the queue. And if you pop and there's nothing available, I'm just going to return a default. So you are actually changing the semantics of the queue, and you'll never have a failure case. So even though some of those pushes and pops are kind of technically failures, it's never going to report them as such. And therefore, you get this huge throughput because it just has different behavioral semantics. Now, there's a few more optimizations you could probably do with multiple producers, multiple consumers. You could try pinning a thread to a specific core to avoid kind of cache clearing. However, this is kind of difficult to do on macOS these days. You have these quality of service APIs that kind of provide hints to how the CPU should be utilized, but it's quite difficult to actually pin a thread to a core. And then, as I mentioned, you could do this kind of per thread caching where you kind of take a snapshot of the queue and then try and push and pop that many times without interacting with the other side of the queue. And the other thing you could do is not really in the way I've set things up, but it's quite common to have single producer, multiple consumer queues that kind of push some work onto a queue, and then you have multiple queues trying to pop those operations off and then do some work. Now, if the producer thread has to complete its push, it might, if the queue is full, just be able to read an item off, do the work to make some space to push another item on. So a couple of comparisons kind of drawing this back to the things that we showed at the beginning and why the behaviors matter here is if we compare with locks. So we can pick the best performing level 1, 2, and 3 queues and compare those with using mutexes or real-time mutexes. You can see at each stage the throughput is much higher than using mutexes, so they are a net win generally. However, the throughput at level 1 versus level 2 and level 3 is much, much higher. And it's because this additional complexity and the increased number of atomic operations that you need in order to just be able to deal with multiple threads come at a cost. So despite using multiple producer and multiple consumer threads, we're still not getting as much throughput. So just think about how many threads you need, because you might not be actually getting higher throughput just by throwing more threads at it. And in the same way, we can kind of go back to the serial case where we have no threads and the throughput is way bigger than anything we've ever got. So maybe you don't even need to reach for threads at all. If you're just doing some kind of mathsy type sum, maybe just do it in place. Maybe that's the fastest way to do it because everything's nice there on the stack, hot in cache. And I'm going to do, I think, one final comparison between single producer and multiple consumer queues from the same provider. So here we have a single producer, single consumer benchmark, so just one thread each side, but I'm using Moody Camel's reader writer queue, which only supports single producer, single consumer, and its concurrent queue, which supports multiple producer, multiple consumer operations, but only using one thread. And you can see there's a big difference in throughput just for having the ability that is never used to use multiple threads. And it's the same when we have multiple consumers. If we take farbot in setup as single producer, multiple consumer, and then in its multiple producer configuration, we're paying some penalty here for having set it up effectively incorrectly because we're only ever using one thread. So the message here is pick the right queue for the job. Think about the behaviors you need from this table, whether you're optimizing for throughput or perhaps latency is important to you, particularly whether it's a push or a pop latency, because as we've seen, they can differ. Perhaps memory size is important to you. You're doing some embedded system that has very low memory. Perhaps doing the queue that has the sequence number, which can double the size of your queue actually is a price you don't want to pay. Now, there is a bonus level, and that is the weight-free multiple producer, multiple consumer. Now, I haven't got time to cover this in 5 minutes, but if you want an introduction to what weight-free means, I highly recommend Daniel Anderson's talk, When Lock-Free Still Isn't Enough. Now, he introduces the topic with a different example that essentially shows the kind of patterns that are used in weight-free algorithms. And in weight-free queues, you typically get this idea of having some limit to the number of threads that can ever use the queue, because it kind of stores thread IDs, and then you sort of commit an operation, or you kind of tell the queue that I want to push or pop a value, and then the threads just kind of cooperatively go in and dispatch that work to do. So you might say, I want to push this value on, and then another thread might come along and help it out. And when you have this helping, you typically know you're in sort of weight-free territory. But those queues are horrendously complicated, and you typically get much worse throughput or performance. But the thing that you get is a guarantee for the upper bound of the number of instructions. And when you're doing things where that is important, such as automotive, medical, aerospace, then that's where those queues become applicable. Maybe I'll go into that at some point in the future. Now, I've mentioned a few talks already, but it's also worth noting a few others that kind of inspired this talk and provided some background information. And the first is Christopher Frett's, his Beyond Sequential Consistency. I think he's given that a few times. Jody Haggins has a talk on building robust inter-process queues and what sort of differences and pitfalls to look out for there. And Erez Strauss gave an interesting talk about a multiple producer, multi-consumer queue, but it has a slightly different shape and some slightly different limitations to most of what I showed today. It kind of goes halfway to helping, so it's a sort of introduction to weight-free, I like to think it is. Okay, here, that's the end. I hope you've enjoyed it. I'm just going to have a quick look to see if there are any questions here before I head over to Discord. Let me see if I can get the chat up. I can't see the chat here at the moment, so I think I'm going to head over to not Discord, head over to GatherTown, answer some questions there, and if you've got any more questions, you can add them to Discord and I'll try and get back to you. So yeah, if you want to see any of my past talks or presentations, and also the slides will be available on my GitHub as well. Okay, thanks very much.